Hello. So actually, there was one item I want to cover. This won't take long, maybe 5-10 minutes at most, and that basically wraps up this this lecture series from chapter 9, um, at least for looking at the two sample tests, both the paired and the independent test. So the pair test. It's really nice because it's clean, it's easy. But unfortunately, for the two sample test, where we have independent populations and they're not paired, we need to be careful about making sure these variances are equal. That was our case one, right? And then case two was where they were actually different, where we had to use Welch's test. So, in addition to looking at the output that we get from SPSS and looking at Levine's test, and this is Levine's test. So just as an aside, Levine's test uses what's called the F distribution, which we will eventually learn about. But it's just basically another test statistic that's used when using um, um, tests that involve variances. And so we notice here that we did not reject the null of equal variances because the p-value was fairly large. So we went ahead and assumed equal variability. Excuse me, yes, equal variability. And so another thing is useful to do in addition, just for completeness, is to go to our QQ plot and actually look at the distribution of the QQ plot to see if we're satisfying the normality conditions of each of the populations as well. Okay, it's always fun to do that, because that's something that that was another assumption that we did make for the test. So we should consider that, and because that's not something we've done yet, and I know it is a little bit confusing. It actually confused me. Of course, that's not hard to do, but there's actually two ways to run a QQ plot. One is to go directly here under descriptive statistics. You go to QQ plot, and then we can generate a QQ plot that way with all the nice statistics and graphs and so forth that it gives us. Likewise, Explorer, we can generate some QQ plots here as well. It's a little bit different because here we can actually give it a factor list. The factor list in our case was spider or picture. So our dependent list here, that's our measurement variable, okay, goes there, and then our factor list goes here. And so when we do that, SPSS immediately knows, oh, okay, when I generate the statistics, I'm going to do it for two cases, one for the spider and then one for the picture. And of course, you could have many different factor lists in here. Different factors. Here we only have two. So let's look at some of the plots that we might like to generate. Well, clearly I want the normality plot with tests. Spread versus level with Levine test. Not concerned with that right now. We could do a stem and leaf, and we can do a histogram. We'll just go and leave those. Maybe we'll look at them. And dependent together, histogram. Let's continue, because there's only a few data points, so histogram really wouldn't make sense. Perhaps a stem and leaf would. So options, that's okay. And bootstrap. Let's see, we want both plots and statistics, so let's see what happens. Okay. Case processing summaries, just telling us what were valid data points are missing. We had good data there, nothing's missing. We have some descriptive statistics, you can look at that. This is actually kind of nice. It gives us trim means, median variances, maximum, mins, ranges, interquartile range, which we know what that is. That's the difference of the 75th percentile and the 25th percentile. Gives us an idea of spread. And here's the tests for normality. Kolmogorov. And so there's actually two tests for normality run. One with the data corresponding to picture, and one with the data corresponding to the real um, spider. And remember the tests for normality under Levine, test of normality for Kolmogorov-Smirnov and Shapiro-Wilks is that under the null we assume normality, and the alternative is not normal. So high p-values, 0.2, it's larger than 0.05, say, indicate do not reject, right? We only reject when p-value is small. So that means we can go ahead and just accept normality of the data for both factors, picture and real spider. And it's still thinking. And a QQ plot, which I think are very, very powerful. Always generate a QQ plot when trying to assess normality. And as you see here, yeah, there's a real slight, you can argue, S. You get good at reading these. The S would have to be really marked for you to say, well, I don't really like, the looks of that. That doesn't look normal. But these minor deviations from the line are okay. They're acceptable. Even though you have 3 here that are above and 3 here that are below, it's still okay. And that's consistent with what we're seeing up here with our significance on the Kolmogorov-Smirnov test there. And that's for the picture, and this is for the spider. Again, if you don't see a marked pattern, as I mentioned before, where you have heavy tails here, say, and then heavy tails here, and things are just kind of scattered about the line in this type of fashion, then that's fine. You can assume normality, no strong deviations there. And I don't really work with the trended or detrended. I just work with these. And so let's just skip these trended there. This is really, really nice too. I love box plots. You guys know that. I think they're really, really, really great in displaying the distribution of the data. And this is really cool because, look, you're seeing everything here in one shot. You're seeing the data for the picture and then the data for the real spider and the anxiety levels. And you can see that these whiskers, extend up to, where the data is still consistent with the underlying profile. Likewise here, I would say, yeah, they're both very symmetric, even though the median is a little higher here. That's fine. So this is very consistent with what we saw earlier with the QQ plot, because you'd see, well, this would be, yes, probably mound-shaped because it's very symmetric. The median's right in the center, and likewise here. Another thing is, if you're trying to compare, you'll notice that there's not significant difference in the overlap in these two boxes. Generally, the rule of thumb, if there's slight overlap, or considerable overlap between the two boxes, then you generally not reject that the means are different. Okay, again, that's a kind of a rule of thumb that holds quite often. Now, if this box had been shifted a lot higher, say, and the bottom of the box was here, say, or even here where there was slight overlap between the two boxes, then that would be strong indication that the means would actually be different between the two populations. So this is all consistent with what we've seen so far in terms of the t-test, in terms of the normality test, and also in terms of the variability. Just looking at these graphs, you can argue that, wow, the variability is quite similar. There's not enough evidence to say that the variability should be different, and that's something else we determined from our Levine's test. So that concludes this session. I guess I went a lot longer than 5 minutes. That's just because I really like this stuff, and I'm having fun. So I hope you guys had fun too, and we'll see you on Tuesday. Thank you very much. Bye.